So now we understand why is it that the antipedal triangle undergoes inversions, namely when P is contained in one of the midlines, right, of my reference triangle. That's fine. I actually want in this video to look at the locus of a few triangle centers of my antipedal magenta triangle, starting with the barycenter. Okay, so here's the barycenter. We can investigate what this guy's going to do over rotations of the inner triangle. But before we do this, let's actually look at the locus of x2 over motions of P about the circumcircle. So as I move P on my circumcircle, x2 is executing this intricate motion that is not of great interest to us. So I'm going to turn it off. This is the locus of x2 of my antipedal with a stationary blue triangle and with rotating P, right? So if I scale this out, so you get an idea of what this is a stellated locus. This is not the main focus of the series of videos. We actually want to investigate what's the loci of, another thing that we can ask before I say that is what's the locus of the vertices of my antipedal triangle as I move the family. So you get, again, you get this interesting combination of something with a loop, and all the three vertices are actually going through the same unbounded locus. Okay, but again, this is not germane. Let's talk about what's the most central question here, and property is, what is the locus of x2 as I rotate my equilateral family, x2 of the antipedals? So let's draw that. It turns out that if P is anywhere on the plane, the locus of x2 is always a hyperbola. And there's a few special cases, okay? So here's the locus of x2 for a rotating family of equilateral triangles, a hyperbola. Okay, let's move P away from the circumcircle just a tad, right there. Because everything is projective, the locus of x2 remains a hyperbola, okay? Let's move now P inside the circumcircle, still a hyperbola, and then we get a very nice phenomenon. You can see here that this hyperbola is straightening out as P approaches the incircle. When P is on the incircle, and let's actually just move it a tad outside of the incircle so we actually see a phenomenon. There you go. So the straightening out phenomenon is going to cause the two branches of the hyperbola to actually become at some point parallel. Now there's a secondary effect here, which is while x2 is moving along that outer branch in a decent speed, when the antecedent executes or undergoes that inversion, you can see here that one of the midlines is pretty close to P, okay? When the antecedent undergoes an inversion, x4 exchanges branches and it reappears on the bottom here, but it's actually going to move on this bottom branch at very high speed. Okay, it's going to move at a much higher speed than it's actually moving on the outer branch. So much so that when P is actually on the incircle, the speed is so great that it cannot be drawn, and that branch virtually disappears. So then we can actually say or make this sort of approximation that the locus of x2, if P is on the incircle, is a line. In other words, when there's an inversion, you're just going through at infinite speed through the virtual invisible branch, and you very quickly reappear on the top branch at reasonable speed. So this is really two parallel lines where the second branch is invisible. Still a hyperbola. Okay. Now what happens if P enters the incircle? Let's see, if I enter the incircle, I remain a hyperbola. Okay, I remain a hyperbola, and it looks like there is, oh, that's interesting, I wasn't aware of that. There is a particular distance between P, because I'm still a hyperbola here, right? Between P and the center, where this thing becomes an ellipse. And I wasn't aware of that. Okay, now this is a mysterious threshold, right? What is the threshold? And it looks like could be that this threshold is basically the in radius to the medial triangle. It looks like P here is internal to the incircle of the medial triangle, and therefore we're getting an elliptic locus for x2 but if I actually jog P just slightly outwards here so that it's exterior to the not shown incircle of the medial, I believe, yes, at this position, so at exactly point 0.25, you can see here that now x2, the locus of x2 is a parabola. And above it, the locus of x2 goes back to being a hyperbola. Although I know this, there's going to be another branch there. So that's quite interesting, right? Let's recap the states of x2. If I am on the outer conic, the locus of x2, of my Sevian family is a hyperbola, not regular, not rectangular. Different axes here. One of the axes has this nice number. The minor axis is 0.8, where this means 0.8 of the circumradius of the original family. This hyperbola is tangent to the circumcircle at P. If r is greater than the circumradius, greater than 1, I'm still a hyperbola. Okay, still a hyperbola. And then if I go inside the circumcircle, I remain a hyperbola, but then I'm approaching that degenerate two parallel line hyperbola. And when P is actually on the incircle, one of the branches virtually becomes a virtual branch because x4 is just zipping through it at infinite speed. And you could argue here that the locus of x2 is a line, is a straight line. That's quite nice, right? The locus of x2 is a straight line. If I actually vary P, that locus is going to envelop, by symmetry here, I would hazard to say a circle. Okay, and now you have this really cool thing that I just realized while I was talking to you guys. That now if I go inside the incircle, I go back to being a hyperbola. Right here, I'm still a hyperbola. However, if P is in the interior of the incircle to the medial, this hyperbola turns into an ellipse. That's quite nice. So here's the ellipse. By the way, is this ellipse going to survive an affine transformation? Yes. Everything here survives affine transformations because with x2, everything's projectively invariant. Okay, so this construction actually survives projectivities, right? Now, what is new to me here is that if I make P be on the incircle of the medial, meaning if you think of the circumradius as being equal to 1, the in radius is equal to half, and the in radius of the medial is going to be equal to 1/4. So when this distance from the common center to P is 1/4 of the circumradius, that is to say I'm on the incircle of my medial, the locus of x2 is at the transition to a parabola. And if you go further in, and by the way, I would love to know where the focus of this parabola is. Unfortunately, I'm not drawing it here, but I wouldn't be surprised if this is something very harmonious, such as, it's going to be on the circumcircle. And if I go inside, it's an ellipse. That's quite nice. It's never a circle. It's always an ellipse. And then you get into this situation here. Can it ever be a rectangular hyperbola? Let's investigate that. It looks like it can. So here's another question that we should leave as an exercise, but there's a particular distance, and I'm approaching it here, say at 1.2, let's say. It's less than that, 1.18, 1.19. Yeah, somewhere around here, 1.191, 19.2, 8.9, 8.8. Let's try to get this by hand. Yeah, that's pretty close, right? 8.7. Yeah, now it's too much. So near 1.188, and that what I mean by that is the distance of P to the common center, where circumradius is equal to 1. You can see here that there is a particular setting where this locus is going to be a rectangular hyperbola. Okay, guys, so I'll see you on the next video. We'll talk about more phenomena related to loci of triangle centers of Sievian triangles. Sorry, anti-Sievian triangles. See you on the next video.